Welcome to Physics Hub. As you know that I have shared short notes on solid state physics. Now today I will be sharing with you the short notes on electronics. I will not cover the whole electronics, but in this video I will try to cover the analog part. The digital part will be covered in some other video. So let's start. It starts with the Fermi-Dirac distribution function f of e equals to 1 by 1 plus e to the power e minus ef by kt, and f at ef equals to half. F at ef plus delta E means above the Fermi energy level with some energy interval delta E equals to 1 minus f of ef minus delta E. Now in here I have shown you some graph. What happening? Schematic band diagrams. So the left one for intrinsic one EC, EV, and this is a Fermi level, and another plots have been shown. As you can see from here, this is the band diagram of p-type, n-type at intrinsic semiconductor, and this is energy density of states along x-axis, and along y-axis energy we have plotted in this way. This is for intrinsic, this is for n-type, this is for p-type. So as you can see, the Fermi level is lying close to the valence band in case of p-type, and the Fermi level is lying close to the conduction band in case of n-type, and in case of intrinsic semiconductor the Fermi level is lying in between conduction band and valence band. And this plot is E versus Fe. Okay, so as you can see, it is the Fermi energy is cutting at the middle in each and every cases, in case of intrinsic, in case of n-type, and in case of p-type also. And this is carrier concentration along x-axis, and as you can see, it is filled with valence band is filled with electrons, and conduction band is filled with lesser electron. You can see it, but for n-type electrons are more in conduction band, and for intrinsic the concentration of electrons and holes are same. Now Pn equals to Ni square in all the cases. This is called law of mass action. KCL sum of I equals to 0. At any particular node the sum of currents is 0. So for this case you can see I1 plus I2 minus I3 minus I4 minus I5 equals to 0. Now how to determine the sign? Current entering into the junction is taken to be positive, and current leaving the junction is taken to be negative. Now KVL is the sum of voltage drop along some mesh or loop is 0. And how to take the voltage drop? Voltage drop equals to I into R is negative when you go in the direction of current, and delta V equals to IR is positive when you go in the opposite direction of current. And for voltage source, delta V equals to plus C when you go from the negative terminal to positive terminal. Then if you are sensing in this way from negative to positive, then the potential drop should be taken to be positive. And when you are going from positive to negative, then delta V, or means voltage drop, should be taken to be negative. Now Thevenin's theorem and Norton's theorem, these two theorems are very important. So Thevenin theorem, suppose this is the main circuit, then if you find out the equivalent circuit, then you will get this. And in this circuit, ETH means Thevenin equivalent voltage equals to E by R1 plus R2 into R2, and RTH equal to R1 R2 by R1 plus R2 plus R3. This is active circuit, and this is the Thevenin equivalent circuit. Voltage source and a resistance in series. In case of Norton's, we see that a current source with a resistance in parallel, and the relationship between Norton's theorem and Thevenin's theorem is given by this relationship: ETH equals to IN into RN. Okay. Here current source and a resistance in parallel, as I told. Now maximum power transfer theorem. Maximum power is transferred when load resistance RL equals to internal resistance of the source. When this condition holds, then we get the maximum power transfer. Efficiency of power transfer equals to P load by P input into 100%. Load means this resistance RL. Electron and hole densities in intrinsic semiconductors. N equals to Nc exponential minus Ec minus Ef by Kt, and P equals to Nb exponential minus Ef minus Eb by Kt. Nc equals to 2 into 2 pi Me star Kt by h square to the power 3 by 2. Nb equals to 2 into 2 pi Mh star Kt by h square to the power 3 by 2. And this is law of mass action, as I have already told. For intrinsic semiconductor, EF equals to EC plus EB by 2 plus 3 KT by 4 ln MH star by ME star. This formula is frequently used to solve problems. Mobility mu is the average drift velocity VDC per unit electric field, means mu equals to VDC by E, and the unit is meter square volt inverse. Second inverse. Conductivity sigma equals to E into N mu N plus P mu P equals to 1 by rho. Rho is the resistivity. Drift current density ZD equals to sigma into E. Sigma equals to E into N mu N plus P mu P, and E is E. So ZD equals to this. So this formula is also very important. Ni equals to root over N into P equals root over NCNB to the power minus EC minus EB by 2 KT. This is for intrinsic semiconductor, equals to 2 into 2 pi KT by h square to the power 3 by 2 ME star MH star to the power 3 by 2 3 by 4 e to the power minus EG by twice KT. Me star and Mh star are the effective masses of electrons and holes respectively. Therefore, sigma equals to E into Ni into mu N plus mu P equals to twice E into 2 pi KT by h square to the power 3 by 2 Me star Mh star to the power 3 by 4 e to the power minus Eg by twice KT into mu N plus mu P. These things can be written as A into e to the power minus Eg by twice KT, where A is this thing. And if we plot ln sigma versus 1 by T, then we get a straight line, and if the intersection at the y-axis is ln A. Ln sigma equals to ln A minus Eg by twice KT. For extrinsic semiconductor, if we plot ln sigma versus 1 by T, then we get this type of curve. So DC portion gives you the intrinsic character, but CBA, this portion, gives you the extrinsic character, or ABC, whatever you call. Mobility and momentum relaxation time tau. E into E equals to M star V by tau. E is the electric field. Mu equals to V by E equals to E into tau by M star. V by E equals to E into tau by M star. Wheatstone bridge, as you can see, R1, R2, R3, R4 and galvanometer is set between the points D and B. Now when equilibrium or balance condition is reached, then current through this portion will be 0, and major voltage Vg equals to 0, means no current is flowing through this, and the condition will be maintained if P by Q, this alternate ratio of this alternate resistances, will be equals to R by S, means these two resistances. Now as you can see, x equal to 0, x equal to x, the density of holes P0 and density of hole at x is Px, and Jp is the whole current density. Jp equals to minus Q into dP by dP dx. dP dx is the gradient of hole. dP is the diffusion coefficient for hole. Similarly for electron, Jn Q into dn by into dn dx. Okay. Now dP dx is itself negative, that's why a minus sign is there, but dn dx is itself negative, but Q is also negative, so it's positive. Current density is to be taken to be positive. Therefore total current density J equals to J drift plus J diffusion, and this is a drift current, as I have already mentioned, and J diffusion is as you have seen from here. So the total current density J is like this. Now Einstein relationship dn by mu n equals to dp by mu p equals to kt by e, where k is the Boltzmann constant. Vt equals to kt by e equals to T by 11600 volt equal to 0.026 volt at room temperature, means at 300 Kelvin. This value should be remembered. It very often you must have encountered this type of value very often while solving the problems. Diffusion length for electrons and holes, Ln equals root over dn tau n, Lp equals root over dp tau p. Now what is diffusion length? Diffusion length is the length which an electron or a hole travels after generating two recombination. Suppose some electron and hole pairs are generated. Now before recombining, the distance they travels is called the diffusion length. Okay. Effect of temperature and doping on mobility. So if you plot mu versus t, you will get t to, this is varying t to the power 3 by 2 and this is varying t to the power minus 3 by 2. This is for impurity scattering, this is for lattice scattering. Okay. Now the potential variation within a graded semiconductor. So this is x1, x2, p1, p2, v1, v2. This is voltage, this is a hole density, and similarly for the electron. P type, this is N type, this is junction, Na, Nd, x1, x2, v1, v2. v1, v2 are the voltage. So graded semiconductor Px is not constant, therefore the voltage difference V21 equals to V2 minus V1 equals to Vt ln P1 by P2. Vt equals to Kt by E equals to T by 11600 volt, and built-in potential for this junction is V0 equals to V21 equals to Vt ln Na Nd by Ni square. So as you can see, these two junctions, two different things, and the built-in potential for these two cases are different. This is Vt ln P1 by P2, but here it is Vt ln Na Nd by Ni square. Ni is the intrinsic carrier concentration. This is a diode equation. I goes to I naught exponential EV by eta kt minus 1. This is for silicon, germanium, silicon, and the cut-in voltage is for germanium it's 0.3 volt and for silicon it's 0.7 volt. Eta means ideality factor equals to 1 for germanium and eta equals to 2 for silicon. This is forward bias, this is reverse bias. Diode resistance, two type of resistances are there: DC resistance or static resistance, and AC resistance or dynamic resistance. So as you can see, R1 equals to V1 by I1, R2 equals to V2 by I3, R3 equals to V3 by I3. This is DC resistance. But when we are calculating AC resistance or dynamic resistance, and R equals to dV by di. I equals to I naught exponential EV by eta kt minus 1. So if you take derivative, you get I into E by eta kt. If you neglect I naught with respect to I, then the AC resistance R equals to eta kt by I into E. So kt by equals to Vt, so eta Vt by I. Diode capacitance, space charge or transition capacitance Ct. So if you have a PN junction, then you can see a depletion region which is depleted of mobile charge carriers, and you get space charge, negative, positive. These are space charge, and if you apply bias, then these space charges can be separated. So accordingly you get space charge or transition capacitance Ct equals to dq dV equals to epsilon A by D. This formula is very important. Diffusion capacitance Cd equals to dq dV equals to d dB by q equals to I into T, means tau. Tau into di dB means tau by R. This is the resistance di dB. So CD equals to tau by R. Half wave rectifier. So this is output current IL equals to Im sin omega t. You are giving some sinusoidal input, and this is the half wave rectifier. This is transformer, and you have inserted a diode here. So this is the input, and you get output, means 0 to pi, 2 pi to 3 pi. So one thing is missing here, so it's half wave rectifier, and the IDC value is Im by pi, and IRMS value equal to Im by 2, and Im equals to Vm by Rf plus RL. Ripple factor for this half wave rectifier case, root over IRMS square minus IDC square by IDC. For half wave rectifier, gamma equals to 1.21. Rectification efficiency eta equals to PDC by Pi into 100%. For full wave rectifier, get this type of circuit diagram, and IDC in this case equals to twice Im by pi, so double of this. IRM is equal to I maximum by root 2, and as you can see, it was missing in case of half wave rectifier, but here you get, in this case of full wave rectifier, you get the full waveform. PIV peak inverse voltage or PRV peak reverse voltage rating. The voltage rating that must not be exceeded in the reverse bias region is the peak inverse voltage. For half wave rectifier, PIV equals to Vm. For full wave rectifier, PIV equals to twice Vm. Zener diode. For Zener diode, you get this kind of circuit diagram, and as you know that Zener diode maintains a constant voltage across it, and the other things are monitored according to this. nature. So Rs minimum equals to Vi maximum minus Vz by Izm. Vz is the voltage drop along this Zener diode. Rs maximum equals to Vi minimum minus Vz by Izk, knee value of the current, plus IL maximum load current, equals to Vi minimum minus Vz by IL max. Izk, the knee current of Zener. If Iz goes below Izk, then the Zener fails to regulate the output voltage. Transition capacitance Ct for varactors or voltage variable capacitance. Abrupt or step graded junction Ct for alloy junction, Ct equals to Vt to the power minus half. Vt effective barrier potential equal to intrinsic potential Vb plus applied reverse bias. Linear graded junction, for linear graded junction we get Ct equals to Vt to the power minus 1 by 3. Okay, so if we write Ct is proportional to 1 by Vt to the power 1 by n, then n equals to 2 for abrupt or step graded junction and n equals to 3 for linear graded junction. For photovoltaic cell or solar cell, this is the schematic diagram of photovoltaic cell. As you can see, this is junction, this is N, P, and reflective glass, outer contact, metal contact, and light intensity. If you plot VOCO or IOC with light intensity, then you will get this. OC means open circuit and AC means short circuit. So as you can see, in case of dark condition, we got I equals to I naught exponential EV by eta kt minus 1, this portion only, but for this photovoltaic cell you get an extra term minus IPH. So in an open circuit condition, this I is 0, therefore current should be 0, means this is 0, and from here you get V0C open circuit KT by E ln 1 plus IPH by I naught. So using this formula you may be asked for any numerical on this topic. Sorry. The short circuit current ISC equals to minus of I naught plus IPH. So light intensity, when no light is there, it was passing through the origin, but when you have light, then you can see at zero bias you are getting some current, some magnitude, although it's negative, but it's still a magnitude, not 0. Okay. Light emitting diode or LED. Physical principle underlying the operation of LED is the emission of radiation due to recombination of holes and electrons. So this is PN junction, and LED works on this principle of recombination of holes and electron, and I is Vi minus Vd by Rs. This is so simple. LED have very low reverse breakdown voltage, typically between 3 volt and 5 volt. Number of images formed by two inclined mirrors. This has come by some mistake, although it's very important. 360 degree by n, 360 degree by theta, and if n is odd, then for a symmetric body, or if the body is placed asymmetrically, number of images will be n, and for symmetric body, number of images will be n minus 1. If n is even, number of images will be n minus 1, irrespective of the nature of the bodies. Power supply rejection ratio PSRR equals to 20 log ripple input by ripple output. In case of LDO, low dropout regulator, PSRR equals to 20 log AB by AB naught. But AB is the open loop gain of the regulator feedback loop, and AB naught is the gain from B input to B output with the regulator feedback loop open. EK diagram. This is direct band graph. As you can see, this is EK direct band graph, and if electron makes transition from conduction band to valence band, then photon emitted. And in case of indirect band, look, in case of direct gap, the conduction band minima and the valence band maxima lies at the same K. But in case of indirect band gap semiconductor, the conduction band minima and valence band maxima doesn't lie at the same K. Absorption coefficient for direct band gap semiconductor is like this, and the indirect gap is a mix of direct plus indirect. Okay, so energy band diagram of for PN heterojunction. So this type of things doesn't come into your GATE or NET exam, but in NET exam syllabus it is there, so you should look at it. So I am trying to make you understand. This is vacuum level, and this is two dissimilar type of semiconductor. This is p type, this is n type, and they have different band gaps. Then how can we get p n heterojunction? So when p and n separated, then the Fermi level, conduction band, valence band are shown in this way, and this is vacuum level, this is conduction band, this is valence band. And similarly for this p type material also, conduction band will be there, valence band will be there, and vacuum level will be there. And this, the difference between the vacuum level and conduction band is the electron affinity, and the difference between the vacuum level and the Fermi level is the work function. Now what happens when you make contact with each other? So this for p n separated, but when you make contact, then we get at thermal equilibrium, when they are in contact, then you get such a spike in the diagram. The logic behind this is at thermal equilibrium the Fermi level must be aligned, so and accordingly the other things are set. Okay, band gap cannot change, that's why you get a spike like this to get a constant band gap. Now when you apply some bias, then some process happens, and you get this under forward bias. So I don't think this type of problem will come, but those who are interested can look at it once. Okay, moving forward, this is for the previous one was for p n heterojunction, this is for p heterojunction. Okay, the same thing, you can, in the same way we can draw the energy band diagrams. Okay, now coming to an important thing, bipolar junction transistor. So emitter, collector, base, PNP. So as you can see, this base section is very narrow, this collector section is broad, but this emitter section is medium. Same case NPN. This is PNP. N to P means PNP. P to N, base should be taken positive. So look, N to P, PNP, P to N, NPN. Emitter, base, collector, size medium, thin, wide. Doping level, emitter is heavily doped, base is very lightly doped, collector is medium. Energy band diagram for a transistor: speed emitter, collector, unbiased condition, N base. So this is neutral condition, unbiased condition. Under biasing, the Fermi level will shift and we will get this EVB plus EVCB. VB is the intrinsic potential barrier at the two junction. Okay, this is for NPN transistor, the same thing, you can check it out. Now three modes of configuration or connections of a transistors. Firstly, common base, then common emitter, common collector. For PNP you get this. I don't need to explain this. NPN. Okay, here it is common base, so base will lie here in the middle. Common emitter will lie in the middle. Common collector will lie at the middle. In this way we can think of it. And one thing you should remember, that emitter is forward biased, collector is reverse biased. If you take care of these two things, then it is easier to draw these connections. Okay, so this table is very important. Transistor configuration: common base, common emitter, and common collector, emitter follower. Voltage gain high, medium, low. Current gain low, medium, high. Power gain low, high, medium. Input or output phase relation for common base is 0 degree, common emitter 180 degree, common collector 0 degree. Input resistance low, medium, high. Output resistance high, medium, low. So this table is very important, you write it down. Transistor alpha and beta, alpha C equals to alpha IE plus ICB or by saturation current, alpha DC equal to IC by IE. IC equal to alpha E, alpha IC equal to delta IC by delta E at VCB equals to constant. Beta equals to alpha by 1 minus alpha. Beta DC or HF equals to IC by IB. Beta AC or HF equals to delta IC by delta IB at VC equal to constant. Beta is much greater than 1 for a good transistor alpha equal to alpha DC equal to alpha AC, and almost and all must be as close to unity as possible. Emitter based junction, collector based junction, forward, this is called saturation. Forward reverse active region, reverse cutoff, and reverse forward, then it is inverted. Since electron mobility is far greater than hole mobility, an NPN transistor can be operated over high frequencies than a PNP transistors. CBC characteristics of an NPN transistor, you just look into it. This is CB mode, this is C mode, and it is input. Input means, look here, you get IE and VBE, VEB. So this is input. Same here IB versus VBE, and output section IC versus VCB. Here IC versus VCE. Okay. The graphs are almost looking similar, but there is something slight difference. You can make it out. CB is suitable for high frequency application. C is audio frequency amplifier. CC for buffer amplifier, used to avoid loading effect. Transistor as a switch. When the transistor is saturated, it is like a closed switch, and when the transistor is cut off, it is like an open switch. Okay, so this is the transistor as a switch. If you are asked to show how transistor acts as a switch, then you should show this type of diagram. In some of the interview, I was asked this question: transistor as a switch, how can you explain to that? So from this you can see that is closed switch, is open switch. If IB is greater than IB saturation, then the operating point Q is at the upper end of the load line and the transistor acts as a closed switch. If IB equals to 0, then the output is plus VCC and the transistor acts as an open switch. Now fixed bias arrangement. So the biasing is fixed and it is fed by two resistors RB and RC. So this is a fixed bias arrangement circuit, and the calculations are trivial, so I am not going to explain this. This circuit cannot achieve stability of Q point against temperature. This is the drawback of this fixed bias arrangement. Now voltage divider or self bias. So as you can see, this is divided into two R section, R1 and R2, and this circuit is called voltage divider. CE is the bypass capacitors, C1 C2 are the coupling capacitors. Now to simplify this circuit, we use Thevenin's theorem and we got this. So this type of circuit you have very frequently encountered in your examination. So if you want to note down, you pause the video and note it down. Okay, I have written it in a simplified language. This is for collector base feedback bias. Okay, so I could not make it shorter, so although it's a short note, but still it cannot be made shorter, otherwise nothing will be there. So this is a circuit and the minimum explanation. Collector base feedback bias. RB is connected directly between the base and the collector junction of the transistor, and it provides a negative voltage shunt feedback from collector to base circuit and improves the stability of Q point over that of the fixed bias arrangement. So this is the improved version of the fixed bias arrangement. Okay, bias compensation circuit. This is another circuit, not so important, still you should remember. We just read once. Okay, so now we are going to enter into a very important section, FET. Input impedance of FET is very high compared to that of BJT. FET is voltage control device, and whereas the BJT is basically a current control device. The main disadvantage with FET is it's relatively low gain bandwidth product as compared to BJT. JFET, the schematic diagram is shown in this. Say N channel JFET, this is P channel JFET. Okay, this is the channel and this is the highly doped region. Here it is N plus type, this is P plus type. So when the channel is N type, then it is called N channel JFET, and when the channel is P type, then it is called P channel JFET. Now how to remember this, the arrow in which direction the arrow should be directed. Source through which majority carriers enters into the terminal, that is source, and drain through which majority carriers leave the terminals. Static characteristics of JFET and DC biasing. Okay, ID versus VDS, and it shows characteristics like this: locus of pinch of saturation region, this is linear region, this is cutoff, this is drain characteristics, and this part is breakdown. Between pinch off point and breakdown, the JFET acts like a constant current source. Look, this current is constant, maintaining a constant, that's why it is called a constant current source. RDS equals to RDSO divided by 1 minus VGS by VP whole square. RDSO equals to VP by IDSS is the ohmic DC resistance of the JFET when operated in the ohmic region with VGS equal to 0. Transfer characteristics curve of a JFET, ID equal to IDSS into 1 minus VGS by VP whole square, and the graphs look like this. AC resistance between drain and source terminal. Drain resistance RD equals to delta VDS by delta ID, VGS equal to constant. Mutual conductance GM equals to delta ID by delta VGS at VDS equal to constant. Look, that what I was talking about. Entering into the gate means N channel, and in leaving the gate is P channel. Okay, so it is leaving, so it must be P type, and this is entering, so it is N type. This one line help you to remember the things. Mu amplification factor, mu equals to minus delta VDS by delta VGS at ID equals to constant. Fixed bias arrangement for N channel JFET. So as I have discussed about the taking BJT, now you can also design fixed bias arrangement using JFET, and this is the circuit diagram. Similarly, voltage divider bias arrangement can also be done using JFET in this way, and this is important: width of depletion region. This Wx equal to twice epsilon by E and D Vx to the power half. E equal to absolute permittivity of the channel material. Nd is the donor impurity concentration. V of x equal to applied reverse bias potential across space region at x. A equals to 0 bias channel half width. W of x equal to A minus B of x, where Vx equal to Vgs of equal to Vp, then Bx equal to B equals to 0. Therefore, Wx equal to twice E by E and D into Vx means A equals to root over twice E by E and D into Vp. For P type channel JFET, Nd should be replaced by Nm. This is for N channel, and for T type channel, this Nd should be replaced by Na, and other things will remain same. MOSFET. Two type of MOSFET are the enhancement MOSFET, depletion MOSFET. An electric field is established by applying a voltage to the gate. That's why the name MOS field. Metal oxide field effect transistor. Enhancement MOSFET and depletion MOSFET. Okay, this is generally or usually 1. This is generally off, or I have told the opposite thing. Okay, let's see. The oxide layer makes the input resistance of the device to be extremely large, of the order of 10 to the power 10 to 10 to the power 15 ohm. This is the N channel enhancement MOSFET. This is N channel depletion MOSFET. This P substrate, source, gate, drain. Source, gate, drain. This is the SiO2 layer. It is known normally of transistors. This is known normally 1 transistors. Saturation region occurs at large VDS. As the drain voltage increases, the difference in voltage between the drain and the gate becomes smaller. At some point, the difference is too small to maintain the channel near the drain, means pinch off. This is simplified version of MOSFET. Saturation regions occur at VDS greater than VGS minus VT. So this graph is important. This is triode graph. Enough negative gate voltage can cause the channel depleted of majority carriers and cut off the current between the source and the drain. The least negative gate voltage causing this is called the gate source cutoff voltage or threshold voltage VT. Some relations are given in this equation ID equals to twice k into VGS minus VT into VDS. So ohmic region ID versus VGS looks like this. ID saturation equals to k into VGS minus VT whole square. This is for saturation region. This applies for ohmic region, and this is the ID versus VDS graph. Okay, so this is all for today, guys. If you find this video helpful, please give it a thumbs up, and to get more such videos on physics and to get updated, to stay updated about different competitive exams on physics on national level, then you can subscribe our channel. And if you subscribe the channel, don't forget to press the bell icon. And finally, what I say, thanks for watching.